So here's something worth thinking about while you're lying there, getting comfortable, letting the day wind down. Right now, wherever you are, you're being pulled toward the center of the earth. You can feel it, that gentle pressure of your body against the mattress, the weight of your arms, the heaviness settling into your legs. Gravity, the most obvious force in the universe, the one we notice first as babies and stop thinking about entirely as adults. And yet, for all its familiarity, gravity turns out to be the strangest thing in physics, stranger than quantum mechanics, stranger than dark matter, stranger than anything you've probably heard about. Because gravity, it turns out, isn't really a force at all. And figuring that out, really understanding what gravity actually is, took one person, working mostly alone, about 10 years of the most intense intellectual effort any human being has probably ever sustained. That person was Albert Einstein, and the thing he figured out was general relativity. Now, we're going to take our time with this. There's no rush. The whole point is to let these ideas settle in slowly, like snow falling on a quiet street. Some of this will be familiar. Some of it will surprise you, and some of it might seem impossible at first. But I promise you, it all makes sense. It's one of the most beautiful things human beings have ever figured out, and it's worth understanding properly. So let's start at the very beginning. Not with Einstein, not yet, but with the person whose ideas Einstein eventually replaced. Let's start with Isaac Newton, sitting in his study in the 1680s, trying to explain why the moon doesn't fly off into space. Newton's world was a world of forces. Push something, it moves. Stop pushing, it stops. Or at least, it would if there weren't friction and air and all the messy realities of the physical world. Newton cleaned all that up with his laws of motion. An object at rest stays at rest. An object in motion stays in motion unless something acts on it. Force equals mass times acceleration. These were revolutionary ideas in the 17th century, and they still work beautifully for almost everything you encounter in daily life. When you throw a ball, Newton's laws tell you exactly where it's going to land. When you design a bridge, Newton's laws tell you how much weight it can hold. They're spectacularly useful. But Newton had a problem. He could describe what gravity does. He could tell you that every object with mass attracts every other object with mass, that the force falls off with the square of the distance between them, that this one simple law explains both the apple falling from the tree and the planets orbiting the sun. He could give you the equation, and that equation would let you predict eclipses and tides and the trajectories of cannonballs with stunning accuracy. But he couldn't tell you how. How does the Earth know the sun is there? How does gravity reach across 93 million miles of empty space and pull on our planet? What is the mechanism? And this bothered Newton. It really did. There's a famous passage in a letter he wrote to Richard Bentley in 1693 where he says, and I'm paraphrasing slightly, that the idea of one body acting on another through a vacuum at a distance with nothing in between to carry the force is so absurd that no person who has any competent faculty of thinking could ever fall into it. He's basically saying, I know this doesn't make sense. I know there has to be something more going on, but I can't figure out what it is and the math works, so let's just use it and move on. And that's exactly what the world did for over 200 years. Newton's law of universal gravitation was one of the greatest achievements in the history of science, and it worked so well that almost nobody questioned it. You could use it to discover new planets. That actually happened. In 1846, astronomers noticed that Uranus wasn't quite where Newton's laws said it should be. Its orbit was a little off, a little wobbly. And two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that the wobble could be explained if there was another planet out there, farther from the Sun, whose gravity was tugging on Uranus. Le Verrier told an astronomer in Berlin where to point his telescope, and on the very first night of looking, September 23rd, 1846, there it was. Neptune. A planet, discovered not by looking at the sky, but by doing math with Newton's equations. That's how good Newtonian gravity was. But here's the thing. There was one tiny problem that wouldn't go away. Mercury. Mercury is the closest planet to the Sun, and it has this slightly elliptical orbit. Not a perfect circle, but an oval. And the long axis of that oval rotates slowly over time. Imagine an egg lying on a table, and you spin it very slowly, so the pointy end traces a circle. That's roughly what Mercury's orbit does. It's called the precession of the perihelion, which is a fancy way of saying the point where Mercury gets closest to the Sun shifts a little bit with each orbit. Now, most of this precession could be explained perfectly well by Newton's laws. The gravitational pull of the other planets, especially Jupiter and Venus, accounts for almost all of it. But not quite all of it. There was a tiny leftover, about 43 arcseconds per century. That's an incredibly small amount. An arcsecond is 1/3600th of a degree. So we're talking about a discrepancy of roughly 1/100th of a degree per century. Minuscule. Almost nothing. Le Verrier, the same brilliant mathematician who had found Neptune, noticed this discrepancy in 1859, and he tried the same trick that had worked so spectacularly before. He proposed that there must be another planet, even closer to the Sun than Mercury, whose gravity was causing the extra precession. He even gave it a name, Vulcan. And for decades, astronomers searched for Vulcan. Some even claimed to have seen it, dark spots crossing the face of the Sun during eclipses, but it was never confirmed. It wasn't there. The planet didn't exist. So here was this tiny, nagging discrepancy. 43 arcseconds per century. Too small for most people to worry about. But it was real, and it meant that Newton's perfect theory of gravity wasn't quite perfect after all. Something was missing from our understanding of how gravity works. Let's leave that thread hanging for a moment and talk about someone else. A young man in Bern, Switzerland, in 1905. He's 26 years old, he has a newborn son, and he works as a patent clerk, a technical expert, third class, at the Swiss Federal Patent Office. His job is to evaluate patent applications for electromagnetic devices. It's not glamorous work, but it pays the bills, and it leaves him with enough mental energy to think about physics in his spare time. His name, of course, is Albert Einstein. Now, Einstein in 1905 is not the white-haired icon you're picturing. He's young, he has a thick, dark mustache, and he's been struggling. He finished his degree at the Polytechnic in Zurich a few years earlier, but he couldn't get an academic job. His professors didn't think much of him. He'd skipped too many lectures. He was too independent, too argumentative. One of his professors, Hermann Minkowski, actually called him a lazy dog, which is ironic because Minkowski would later make crucial contributions to the mathematical framework of Einstein's own theory. But in 1905, Einstein is nobody. He's a patent clerk with a physics degree and a lot of ideas. And in that single year, 1905, his miracle year, his annus mirabilis, he publishes 4 papers that change physics forever. One of them explains the photoelectric effect and helps launch quantum mechanics. One of them explains Brownian motion and helps prove that atoms are real. And 2 of them lay out what we now call special relativity. Special relativity. Let's talk about what that means, because you can't understand general relativity without understanding special relativity first, and special relativity is itself one of the most mind-bending ideas anyone has ever had. Here's where it starts. There was a problem in physics at the end of the 19th century, and it had to do with light. James Clerk Maxwell, the great Scottish physicist, had shown in the 1860s that light is an electromagnetic wave, a ripple in electric and magnetic fields that travels through space at a specific speed, about 186,000 miles per second, or roughly 300,000 kilometers per second. Maxwell's equations gave you this speed, and it just fell out of the math. It wasn't something you put in. It was something the equations told you. But here's what was strange about it. In Newtonian physics, speeds are always relative. If you're on a train going 60 miles an hour and you throw a ball forward, at 20 miles an hour, someone standing on the platform sees the ball going 80. Speeds add up. That's just common sense. So if light travels at 300,000 kilometers per second, you'd naturally ask, relative to what? If you're moving toward a beam of light, shouldn't you measure it going faster? If you're moving away, shouldn't it seem slower? People tried to measure this. The most famous attempt was the Michelson-Morley experiment in 1887, where Albert Michelson and Edward Morley built an incredibly precise instrument called an interferometer to detect differences in the speed of light as the Earth moved through space. The Earth orbits the Sun at about 30 kilometers per second, so if light has a fixed speed relative to some background medium, what people called the luminiferous ether, then you should be able to detect a difference in the speed of light depending on which direction you measure it. It would be subtle, but Michelson's instrument was sensitive enough to catch it. They found nothing. 0 difference. The speed of light was the same in every direction, no matter how the Earth was moving. It was one of the most important null results in the history of science. Einstein took this seriously, more seriously than almost anyone else. And in his 1905 paper on the electrodynamics of moving bodies, he started from 2 simple postulates. First, the laws of physics are the same for everyone moving at a constant speed. There's no experiment you can do inside a sealed room to tell whether you're moving or standing still, as long as you're not accelerating. And second, the speed of light in a vacuum is the same for all observers, regardless of how they're moving. That second postulate sounds innocent, but think about what it means. If I'm standing still and I measure a beam of light, I get 300,000 kilometers per second. If you're flying toward that same beam at half the speed of light, you also measure 300,000 kilometers per second. Not more. The same. That seems impossible. That seems like it breaks basic arithmetic. If speeds add up the way Newton said they should, this can't be right. But Einstein showed that it is right. And the reason it works is that our basic intuitions about space and time are wrong. Not slightly wrong. Fundamentally wrong. To keep the speed of light constant for all observers, something else has to give. And what gives is time itself. This is where it starts to get beautiful and maybe a little unsettling. Einstein showed that time passes at different rates for people moving at different speeds. If you're moving very fast relative to me, your clocks run slower, as measured by me. Your seconds are longer than my seconds. This isn't an illusion. It's not a trick of perception. It's not that your clock is broken. Time itself, the actual passage of moments, is different for you than it is for me. This is called time dilation, and it's been confirmed by experiments so many times that it's not even controversial anymore. We'll come back to that. He also showed that lengths contract in the direction of motion. Objects physically get shorter when they move fast. And he showed that mass and energy are related by that famous equation, E equals mc squared, which tells you that a tiny amount of mass contains an enormous amount of energy. Because the speed of light squared is such a staggeringly large number. But here's what's important for our story. Special relativity works beautifully for objects moving at constant speeds. It handles light, it handles fast-moving particles, it handles all sorts of things. But it has a glaring limitation. It doesn't handle gravity. It doesn't handle acceleration. Einstein built this gorgeous framework for understanding space and time, and then he looked at it and realized it was incomplete. Because in the real universe, things accelerate all the time. Things fall. Planets curve through space on bent paths. And special relativity had nothing to say about any of that. Einstein knew this almost immediately. And sometime around 1907, sitting in his chair at the patent office in Bern, he had what he later called the happiest thought of his life. It was a simple thought experiment, the kind Einstein loved. No lab equipment, no expensive apparatus, just a person and their imagination. He imagined a man falling off a roof, and he realized that during the fall, the man would feel weightless, completely weightless, not almost weightless, not kind of weightless, genuinely, truly weightless, as if gravity had simply switched off. Because during free fall, there's no floor pushing up against your feet, no chair pressing against your back, nothing to give you that sensation of weight. You and everything around you are falling together at exactly the same rate. And so within your little falling world, it's as if gravity doesn't exist at all. Now think about that for a second, because it sounds almost too simple to matter. A person falling off a roof feels weightless. Okay, sure, that seems obvious. But Einstein saw something much deeper hiding inside that obvious little observation. He realized that if you were sealed inside a box, no windows, no way to peek outside, and you were in free fall, you would have absolutely no experiment you could perform, no measurement you could make that would tell you whether you were falling in a gravitational field or simply floating in deep space, far from any planet or star, with no gravity around at all. The experience would be identical, not similar, identical. There is no physical difference between the two situations. And then he flipped it. Imagine you're in that same sealed box, but now you feel your feet pressed firmly against the floor. You feel weight. You drop a ball, and it falls. Everything behaves exactly as if you're standing in a room on Earth with normal gravity pulling you down. But here's the thing. You could also be in deep space, far from any gravitational source, and the box could be accelerating upward, like being pushed by a rocket engine. That upward acceleration would press you into the floor in exactly the same way gravity does. And again, no experiment you could do inside the box would tell you which situation you're in. Gravity pulling you down and acceleration pushing the floor up into you. They feel the same, they look the same, they are, for all practical and physical purposes, the same. This is the equivalence principle. And Einstein didn't treat it as a curiosity or a coincidence. He treated it as a fundamental law of nature. He said, "Gravity and acceleration are not just similar, they are equivalent. They are the same phenomenon experienced from different perspectives. And that one insight, that one quiet realization in a patent office in Switzerland, became the seed from which all of general relativity would eventually grow." But growing that seed took years, almost a decade actually. And those years were some of the most intellectually grueling of Einstein's life, because the equivalence principle told him what gravity was like. It was like acceleration. But it didn't yet tell him the mathematics, the precise equations, the full theory. He knew the destination, or at least he could feel its shape in the dark. But finding the road there was agonizing. Let's slow down and really sit with the equivalence principle, though, because it leads to something beautiful. Imagine you're in an elevator, a big, spacious elevator, and it's accelerating upward. You feel heavier. Your feet press into the floor. Now imagine a beam of light enters through a tiny hole on one side of the elevator. From the outside, that light beam travels in a perfectly straight line, because that's what light does. But from inside the accelerating elevator, the floor is rushing upward, and by the time the light beam reaches the far wall, the elevator has moved up a tiny bit. So from your perspective inside, the light beam appears to curve downward. It bends. Now here's where the equivalence principle does its magic. If acceleration and gravity are truly equivalent, truly the same thing, then gravity must also bend light. A beam of light passing near a massive object, a star, say, should curve. It should follow a bent path. Not because something is pulling on the light the way you'd pull on a ball with a string, but because the space itself, the very fabric through which the light is traveling, is somehow curved or distorted by the presence of that mass. And this is where Einstein's thinking started to move into territory that was genuinely revolutionary. Because up until this point, everyone, Newton, every physicist, every person who'd ever thought about it, had treated space as a stage. A fixed, rigid, unchanging stage on which the drama of physics plays out. Objects move through space, forces act across space, but space itself just sits there, passive, doing nothing. It's the container. It's the background. It doesn't participate. Einstein was beginning to suspect that space is not a stage. Space is a player. Space itself can bend, stretch, warp, and curve, and when it does, that curvature is what we experience as gravity. Mass doesn't reach out across empty space and pull on other mass through some mysterious force. Instead, mass tells space how to curve, and curved space tells objects how to move. That's the core idea. That's the heart of general relativity, right there, in one sentence. Mass curves space, and curved space guides motion. But saying it in a sentence and actually building the mathematics to describe it, those are very different things. And Einstein, brilliant as he was, didn't have the mathematical tools he needed. Not at first. Here's where the story gets wonderfully human. Einstein was a physicist, not a mathematician. He was extraordinary at physical intuition, at thought experiments, at seeing the deep structure of nature. But the kind of math he needed for general relativity, the geometry of curved spaces, was not something he'd studied in depth. In fact, when he was a student at the ETH in Zurich, the Swiss Federal Polytechnic, he'd had a mathematics professor named Hermann Minkowski. And Einstein, by his own admission, had not been the most diligent student. He skipped lectures. He relied on his friend Marcel Grossman's meticulous notes to pass exams. Minkowski reportedly called Einstein a lazy dog at one point, which is kind of wonderful when you think about it. One of the greatest minds in human history, called a lazy dog by his math teacher. But now, around 1912, Einstein was stuck. He had the physical insight. He knew gravity was geometry. He knew space-time, not just space, but the unified fabric of space and time that Minkowski himself had formalized must be curved by the presence of mass and energy. But he didn't know how to describe curved space-time mathematically. And so he reached out to his old friend Marcel Grossman, who was now a professor of mathematics at ETH, and he essentially said, and I'm paraphrasing here, but this is close to what he actually wrote, "Grossman, you must help me, or else I'll go crazy." And Grossman did help him. He pointed Einstein toward an entire branch of mathematics that had been developed decades earlier by a German mathematician named Bernhard Riemann. Riemann had done something extraordinary back in 1854. He generalized geometry beyond the flat, Euclidean geometry you learned in school. You know the geometry where parallel lines never meet, where the angles of a triangle always add up to 180 degrees, where the shortest distance between 2 points is a straight line. Riemann showed that all of that is just one special case. You can have geometries where space is curved, where parallel lines do eventually converge or diverge, where triangles have angles that add up to more or less than 180 degrees, where the shortest path between 2 points isn't straight at all but follows a curve. Think about the surface of the Earth. If you draw a triangle on a globe, say one corner at the North Pole, one on the equator in South America, one on the equator in Africa, and you measure the angles, they add up to more than 180 degrees. That's because the surface of the Earth is curved. It's not flat Euclidean space. And Riemann had built the mathematical machinery to describe these kinds of curved spaces in any number of dimensions, not just two-dimensional surfaces like the Earth's, but 3, 4, any number you like. He developed something called the Riemann curvature tensor, a mathematical object that completely describes how a space is curved at every point. This was exactly what Einstein needed. Riemann had built the tools 60 years before Einstein needed them, without any idea that they'd one day describe the actual geometry of the universe. There's something almost poetic about that. A mathematician exploring abstract ideas about curved spaces purely for the beauty of the mathematics. And then decades later, a physicist discovering that the universe actually works that way. That nature chose Riemann's geometry as its operating language. But even with Riemann's tools in hand, the work was brutal. Einstein spent the years from roughly 1912 to 1915 wrestling with the mathematics of curved space-time. He made mistakes, significant ones. At one point in 1913, he and Grossman published a paper with field equations that were almost right, but not quite. They didn't have the full general covariance that the theory needed, meaning the equations changed their form depending on what coordinate system you used, which Einstein knew, deep down, couldn't be right. A truly fundamental law of nature should look the same regardless of how you choose to describe your coordinates. That's a principle he held on to fiercely, and it kept pulling him back to the problem even when he thought he'd solved it. There were periods of intense frustration. Einstein wrote letters during these years that are almost painful to read. He talks about being exhausted, about the mathematics being incredibly difficult, about not knowing if he'd ever find the right equations. And remember, during this same period, his personal life was falling apart. His marriage to Mileva Maric was deteriorating. He moved from Zurich to Berlin in 1914, partly for professional reasons. He'd been offered a prestigious position. But the move essentially ended his marriage. Mileva stayed in Zurich with their 2 sons. There's a sadness running underneath these years of intellectual struggle that's easy to overlook when you just focus on the physics. And then, in the fall of 1915, things started to come together. Einstein gave a series of 4 lectures to the Prussian Academy of Sciences in Berlin in November of that year. Each week, he presented a new version of his field equations, each one an improvement on the last. He was literally figuring it out in real time, in front of his colleagues, and he wasn't the only one racing toward the answer. A brilliant German mathematician named David Hilbert was working on the same problem, using a different approach, and the 2 were in correspondence. There's been historical debate about who got to the final equations first. It's a complicated story, and both men deserve enormous credit. But Einstein presented his final, correct field equations on November 25, 1915. And here's what's remarkable about that moment. In the weeks leading up to it, as Einstein was refining his equations, he used them to calculate something very specific. He used his new theory to compute the orbit of Mercury, that same stubborn problem we talked about earlier, the 43 arcseconds per century of extra precession that had baffled astronomers for decades. And when he plugged Mercury's orbit into his equations, the answer came out exactly right. 43 arcseconds, no fudge factors, no hypothetical hidden planets, no adjustments. The theory simply predicted what astronomers had been measuring all along. Einstein later said that when he saw that result, he felt heart palpitations. He was so excited he couldn't work for days, and you can understand why. For years, he'd been groping in the dark, wrestling with impossible mathematics, unsure if he was even on the right track. And then suddenly, his theory reached back across decades and explained a mystery that had defeated every other explanation anyone had tried. That's the kind of moment that changes a person, not just intellectually, but physically. You feel it in your body when something that profound clicks into place. And Einstein felt it. He knew in that moment that he was right. Not because someone told him, not because a committee approved it, but because the universe itself had answered him. The math worked, the mystery dissolved, and the theory that produced that answer was beautiful. Not beautiful in some vague poetic sense, but beautiful in the way that mathematicians and physicists use the word, meaning elegant, economical, inevitable. The field equations of general relativity are compact. You can write them in a single line, and yet packed inside that line is everything: the curvature of space, the flow of time, the behavior of matter, the shape of the cosmos, all of it, encoded in one tight expression. But here's the thing about Mercury's orbit. As thrilling as it was for Einstein, it was what scientists call a post-diction, not a prediction. The anomalous precession was already known. The data already existed. So a skeptic could say, well, maybe Einstein just engineered his equations to fit that particular result. That's not really what happened. The equations were derived from deep physical principles, and the Mercury result fell out naturally. But still, to really convince the world, Einstein needed his theory to predict something new, something nobody had observed yet, or at least something that hadn't been confirmed, something that, if it turned out to be true, could only be explained by general relativity and not by Newton. And he had exactly such a prediction ready. We touched on this idea earlier when we talked about the equivalence principle, the thought experiment with the elevator, where a beam of light bends downward in an accelerating box, and therefore, by equivalence, must also bend in a gravitational field. Einstein had actually made a preliminary prediction about light bending back in 1911, before his theory was complete. He calculated how much a beam of starlight should be deflected as it passes close to the sun. And his 1911 calculation gave a specific number, about 0.87 arc-seconds of deflection. That's a tiny angle, but it's measurable. The problem was that 1911 number was based on an incomplete version of the theory. It only accounted for time curvature, not the full curvature of space. When Einstein completed general relativity in 1915 and redid the calculation with the full field equations, the predicted deflection doubled. It came out to about 1.75 arc-seconds. And this is important because Newton's theory of gravity also predicts some light bending. If you treat light as particles with some effective mass, Newtonian gravity gives you exactly that smaller number, the 0.87 arc-seconds. So the two theories made different predictions. Newton said one thing, Einstein said another, and the difference was a factor of 2. That's a clean, testable distinction. Now, how do you actually observe starlight bending around the sun? Think about the problem for a second. You need to see stars that appear very close to the sun in the sky because the bending effect is strongest for light that just grazes the solar surface. But the sun is, well, the sun. It's blindingly bright. You can't see stars near it during the day. So you need a moment when the sun is in the sky, but its light is blocked. You need a total solar eclipse. And this is where one of the most famous experiments in the history of science comes in, and one of the most compelling human stories. The person at the center of it is Arthur Stanley Eddington, a British astrophysicist. Eddington was a Quaker, a pacifist, and one of the few scientists in England during World War I who actually understood Einstein's theory. That last point matters more than you might think. In 1915, Britain and Germany were at war. Scientific communication between the two countries had essentially broken down. Most British physicists had never even seen Einstein's papers, but a Dutch physicist named Willem de Sitter had sent copies of Einstein's work to Eddington through neutral channels, and Eddington immediately recognized the importance of what Einstein had done. He became one of general relativity's earliest and most passionate advocates in the English-speaking world. Now, Eddington was also in a difficult personal position. As a conscientious objector during the war, he faced the very real possibility of being sent to prison or to a labor camp. The Astronomer Royal, Frank Watson Dyson, intervened on his behalf, arguing that Eddington was essential for a critical scientific expedition, an expedition to observe the total solar eclipse that was coming up on May 29, 1919. Dyson essentially saved Eddington from prison by giving him a scientific mission. And what a mission it was. 2 expeditions were organized. One went to Sobral in northern Brazil. The other, led by Eddington himself, went to the island of Principe, off the west coast of Africa. The goal was simple in concept, but enormously difficult in practice. Photograph the stars visible near the sun during totality, then compare their apparent positions to where those same stars appeared in the night sky months later when the sun was nowhere near them. If Einstein was right, the stars near the sun should appear slightly shifted outward, displaced by the bending of their light as it passed through the curved space around the sun. The logistics were daunting. They had to transport heavy, delicate telescopes and photographic equipment across the ocean, set them up in remote locations, and then get everything working perfectly during the few precious minutes of totality. And the weather was not cooperative. On Principe, it rained on the morning of the eclipse. Eddington later described the tension, the clouds, the waiting, the agonizing uncertainty. When totality arrived, the clouds thinned just enough for him to take photographs, but the conditions were far from ideal. In Sobral, the weather was better, but one of the two telescopes there had a problem. The mirror had been distorted by heat from the sun, and the images from that instrument were blurry and unreliable. So the data was messy. This is real science, right? It's never as clean as the textbooks make it sound. When Eddington analyzed the photographic plates, the results from Principe and from the good telescope at Sobral were consistent with Einstein's prediction. The full 1.75 arc-second deflection, not the Newtonian half-value. The blurry plates from the problematic Sobral telescope actually seemed to favor the smaller Newtonian value. But Eddington set those aside as unreliable, and this decision has been debated by historians ever since. Was Eddington being a good scientist by discarding obviously flawed data? Or was he biased toward the result he wanted? The honest answer is probably a bit of both. Eddington genuinely believed in Einstein's theory, and he genuinely had good reasons to distrust those particular plates. Later, reanalyses of the original data have generally confirmed that Eddington's conclusions were correct, but the margin of error was larger than he publicly acknowledged. None of that mattered in the moment, though. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room was packed. A portrait of Newton looked down from the wall, and Dyson and Eddington stood up and told the world that starlight bends around the sun by exactly the amount Einstein predicted, and that Newton's law of gravity, after more than 2 centuries of unchallenged dominance, was not the final word. The reaction was extraordinary. The next day, the Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." And almost overnight, Einstein went from being a well-known physicist to being the most famous scientist on Earth. He became a global celebrity in a way that no scientist had been before, or arguably has been since. His face appeared on the covers of magazines. He received letters from strangers around the world. He was invited everywhere, asked about everything, treated as an oracle on subjects far beyond physics. And here's something worth sitting with for a moment. The reason the world reacted so strongly wasn't just the science. It was the story. It was 1919. The war had just ended. Millions were dead. Europe was shattered. And here was a German-born scientist whose theory had been confirmed by a British expedition. Former enemies, collaborating through the universal language of mathematics and observation. It was a story about the power of human reason to transcend borders and destruction. People needed that story. They latched onto it. And Einstein, with his wild hair and his gentle eyes and his gift for memorable quotes, became the embodiment of it. But let's come back to the physics, because the confirmation of light bending isn't just a historical milestone. It opens up an entirely new way of thinking about what gravity actually does. When we say that mass curves space, and that light follows curved paths through that space, we're saying something profound about the relationship between geometry and physics. Light always travels along the straightest possible path through whatever space it's in. In flat space, that's a straight line. In curved space, it's a curve, what's called a geodesic. So the light isn't being pulled by the sun the way Newton would have described it. The light is going straight. It's space itself that's curved. The light is just faithfully following the geometry. And this idea, that objects in free fall follow geodesics through curved spacetime, is really the central idea of general relativity, stated in its most compact form. Everything else flows from it. Planets orbit the sun not because an invisible force tugs on them, but because the sun's mass creates a curved geometry, and the planets follow the straightest available paths through that geometry, which happen to be ellipses. The The moon orbits the Earth for the same reason. You're sitting in your chair right now, and the reason you feel weight isn't because gravity is pulling you down. It's because the chair is pushing you up, preventing you from following your natural geodesic, which would be free fall toward the center of the Earth. That push you feel, that pressure on your back or your legs, that's not gravity, that's the chair. Gravity, in Einstein's picture, isn't a force at all. It's geometry. Now, I want to slow down and talk about something that Einstein's theory predicts that is, in some ways, even stranger than curved space. Because space and time aren't separate things in relativity. They're woven together into spacetime. It follows that if mass curves space, it must also affect time. And it does. General relativity predicts that time runs slower in stronger gravitational fields. A clock at the base of a mountain ticks slightly slower than a clock at the summit. A clock on the surface of the Earth ticks slightly slower than a clock in orbit. This isn't a metaphor. It's not that the clocks are malfunctioning. Time itself, the actual passage of moments, the aging of atoms, the ticking of every possible clock, all of it runs slower when you're deeper in a gravitational well. This effect is called gravitational time dilation, and when Einstein first proposed it, it must have seemed almost absurdly abstract. Who could possibly measure such a tiny difference? But here's where the story takes a turn that connects directly to something in your pocket or on your wrist right now. Because gravitational time dilation isn't just real. It's something engineers have to correct for every single day in one of the most widely used technologies on the planet. GPS, the Global Positioning System. Those satellites orbiting above you, the ones your phone is quietly talking to right now even as you lie there, they depend on clocks, extremely precise atomic clocks, each one ticking away onboard satellites roughly 20,000 kilometers above the Earth's surface. And the way GPS works is, in principle, beautifully simple. Each satellite broadcasts a signal that says, essentially, I am here, and the time right now is this. Your phone picks up signals from at least 4 of these satellites, compares the tiny differences in arrival times, and from that, triangulates your position on the Earth's surface. The whole system is really just a timing problem, and the accuracy you need is extraordinary. To pin your location down to within a few meters, you need those clocks to be accurate to within about 20 to 30 nanoseconds. A nanosecond is a billionth of a second. That's the kind of precision we're talking about. Now here's where Einstein walks into the room. Those satellites are moving fast, about 14,000 kilometers per hour. So special relativity says their clocks should tick slightly slower than clocks on the ground because of time dilation due to velocity. That effect makes the satellite clocks lose about 7 microseconds per day relative to ground clocks. But the satellites are also way up high, much farther from the Earth's center, sitting in a weaker gravitational field than you are down on the surface. And general relativity says clocks in weaker gravitational fields tick faster. That effect is bigger. It makes the satellite clocks gain about 45 microseconds per day. So, you've got 2 effects pulling in opposite directions. The velocity effect slows the clocks down by 7 microseconds. The gravitational effect speeds them up by 45. The net result is that the satellite clocks run fast by about 38 microseconds every day compared to clocks on the ground. 38 microseconds. That sounds like nothing, right? But light travels about 300 meters in a single microsecond. So 38 microseconds of uncorrected clock drift would introduce a positioning error of about 11 kilometers per day. 11 kilometers. Your phone would tell you you're in the next town over. By the end of a week, the errors would be catastrophic. The whole system would be useless. So the engineers who designed GPS had to build relativistic corrections directly into the system. Before each satellite is even launched, its onboard clock is deliberately set to tick at a slightly different frequency than ground clocks, pre-adjusted to account for both the special and general relativistic effects. And then there are additional corrections applied in real time as the system operates. Every time you open a map on your phone and that little blue dot appears right where you're standing, you are looking at general relativity in action. Einstein's 1915 theory, the one that seemed so abstract, so mathematical, so far removed from everyday life, it's running in your pocket. That still amazes me. And this is a good moment to step back and appreciate something about how science works, because gravitational time dilation wasn't confirmed right away. Einstein predicted it in 1915, but the technology to measure it directly didn't exist for decades. The first really convincing laboratory test didn't come until 1959, when two physicists at Harvard named Robert Pound and Glenn Rebka carried out one of the most elegant experiments in the history of physics. They used a tower, Jefferson Tower at Harvard, which is only about 22.5 meters tall, not exactly a skyscraper, and they wanted to measure the difference in the rate of time between the top and the bottom of this tower. The predicted difference from general relativity was absurdly small. We're talking about a fractional frequency shift of about 2 parts in 10 to the 15th, 2 parts in 1,000 trillion. To measure something that tiny, they needed an incredibly precise way to compare frequencies, and they found it in a phenomenon that had only recently been discovered, the Mössbauer effect, which allows certain atomic nuclei to emit and absorb gamma rays at extraordinarily precise frequencies with almost no energy lost to recoil. It's like having a tuning fork so perfect that you can detect if someone changes its pitch by 1 part in a trillion. What Pound and Rebka did was place a gamma ray source at the bottom of the tower and a detector at the top. If general relativity was right, the gravitational blue shift, or rather, in this direction, the gravitational redshift as the photons climbed up out of the gravitational well, would shift the frequency of the gamma rays just enough that the detector at the top wouldn't quite absorb them properly. The photons would arrive with slightly less energy, slightly lower frequency, because they'd been climbing against gravity, losing energy as they went. And that's exactly what they found. The measured shift matched Einstein's prediction to within about 10%. A few years later, Pound and his student Snyder refined the experiment and got it down to about 1% agreement. It was a stunning confirmation. Time really does run at different rates at different heights in a gravitational field, and you can measure it across the height of a university building. Think about what that means for a second. The top of your head, right now, is aging very slightly faster than the soles of your feet. The difference is unmeasurably small for a human body. We're talking about femtoseconds over a lifetime. But it's real. It's not a trick. It's not an illusion. The geometry of spacetime near the Earth is very slightly curved, and that curvature means time flows at different rates at different altitudes. And with modern atomic clocks, which have gotten spectacularly precise since Pound and Rebka's day, we can actually measure this effect over height differences of just a few centimeters. In 2010, researchers at the National Institute of Standards and Technology, NIST, in Boulder, Colorado, used optical atomic clocks to detect gravitational time dilation over a height difference of about 33 centimeters, 1 foot. They raised one clock about a foot above the other, and they could see the difference in the rate of time. That's the kind of precision we've reached. Einstein would have been astonished. But gravitational time dilation is just one of the predictions that came out of the field equations. Let's talk about another one that took much longer to confirm, and when it finally was confirmed, it opened an entirely new way of observing the universe. Gravitational waves. This is one of my favorite stories in all of physics, because it stretches from a prediction Einstein himself wasn't sure about through decades of theoretical confusion, a bitter controversy, an engineering challenge that seemed borderline impossible, and finally a detection so precise that it measured a change in distance smaller than the width of a proton. The whole saga is remarkable. Einstein first predicted gravitational waves in 1916, just a year after publishing the field equations. The idea, at its core, is intuitive once you've accepted that gravity is the curvature of space-time. If you have a massive object and it accelerates, say 2 stars orbiting each other, the curvature of space-time around them changes, and those changes ripple outward at the speed of light, like waves spreading across the surface of a pond when you toss in a stone. Space-time itself is the pond. The waves are ripples in the fabric of reality. As a gravitational wave passes through a region of space, it stretches space in one direction and compresses it in the perpendicular direction, then reverses. Stretch, compress, oscillating as it goes. If a gravitational wave passed through this room right now, the room would get very slightly taller and narrower, then shorter and wider, then taller and narrower again, over and over, as the wave moved through. But the amount of stretching we're talking about is almost inconceivably small. For the kinds of gravitational waves we might hope to detect from astronomical sources, the change in length would be on the order of 1 part in 10 to the 21st. 1,000th of the diameter of a proton, over a distance of several kilometers. That's the signal you'd need to find. And here's the thing. Einstein himself went back and forth on whether gravitational waves were real. In 1936, he and his assistant Nathan Rosen actually wrote a paper arguing that gravitational waves didn't exist, that what looked like wave solutions to the field equations were actually mathematical artifacts with singularities that made them unphysical. They submitted the paper to physical review, and the journal sent it out for peer review. One of the first times Einstein had experienced that process actually, and he was furious about it. He wrote an angry letter to the editor saying he hadn't authorized strangers to see the paper before publication. But the anonymous reviewer, who turned out to be a cosmologist named Howard Percy Robertson, had found a genuine error in Einstein and Rosen's argument. Eventually, through a somewhat roundabout path involving Robertson quietly pointing out the mistake to Rosen's new assistant Leopold Infeld, Einstein came to accept that the error was real, revised the paper, and published a corrected version that actually supported the existence of gravitational waves rather than denying them. It's a wonderful example of peer review working exactly as it should, even when the person being reviewed is Albert Einstein. But even after that, the question of whether gravitational waves carried real energy, whether they could actually do physical work, move objects, be detected, remained controversial for decades. There was a famous debate at a conference in Chapel Hill, North Carolina, in 1957, where the physicist Richard Feynman proposed a thought experiment that essentially settled the theoretical question. He imagined a stick with beads on it. If a gravitational wave passes by, the beads slide back and forth along the stick because the wave is stretching and compressing space. The friction of the beads moving against the stick generates heat, Heat is energy. Therefore, the wave must be carrying energy. It was such a simple, elegant argument that it more or less ended the theoretical debate. Gravitational waves are real, they carry energy, and in principle, they can be detected. In principle. Because the practical challenge of actually building a detector sensitive enough to catch these waves was so extreme that it took another 60 years and some of the most extraordinary engineering ever attempted. The instrument that finally did it is called LIGO, the Laser Interferometer Gravitational Wave Observatory, and the story of how it came to exist involves decades of work, internal politics, near cancellations, and a cast of characters who were sometimes brilliant, sometimes difficult, and always operating at the very edge of what technology could do. 3 people in particular sit at the heart of the LIGO story, and their relationships, complicated, fractious, sometimes outright hostile, shaped the entire project. Their names are Rainer Weiss, Kip Thorne, and Ronald Drever. And to understand what they built, you need to understand who they were. Rainer Weiss grew up in New York City, the son of a German physician who'd fled the Nazis. Weiss was a tinkerer from the start, the kind of kid who took apart radios and built electronics in his bedroom. He ended up at MIT, and by the late 1960s, he was teaching a general relativity course there. The story goes that a student asked him how gravitational wave detectors would actually work, and Weiss didn't have a good answer. So he went away and thought about it, really carefully. And in 1972 he published a remarkable paper, more of a technical memo really, that laid out the basic concept of using laser interferometry to detect gravitational waves. The idea was conceptually simple, even if the execution would be anything but. You split a laser beam in 2, send each half down a long perpendicular arm, bounce them off mirrors at the far ends, and recombine them. If a gravitational wave passes through, it stretches space in one direction and compresses it in the other. So one arm gets slightly longer while the other gets slightly shorter. That changes the distance each beam travels, which shifts their interference pattern when they recombine. You're essentially using light as a ruler to measure changes in the length of space itself. Now here's where the numbers get wild, and this is worth sitting with for a moment. The gravitational waves that LIGO was designed to detect would change the length of a 4-kilometer arm by about 1/1000th the diameter of a proton. Let me say that differently. A proton is already unimaginably small. It's about a femtometer across, 10 to the negative 15 meters, and LIGO needed to detect changes 1,000 times smaller than that. We're talking about 10 to the negative 18 meters. That's a measurement precision that, when Weiss first proposed it, seemed borderline insane. Many physicists thought it was flatly impossible. And honestly, you can't blame them. Think about all the things that could create a vibration larger than 1,000th of a proton. A truck driving on a highway 3 miles away. Ocean waves hitting a coastline hundreds of kilometers distant. Thermal vibrations in the mirror molecules themselves. Tiny seismic tremors from the Earth's own geological restlessness. All of these produce motions vastly larger than the signal you're trying to detect. It's like trying to hear a specific whisper during a rock concert, except the whisper is 1,000,000,000 times quieter than that analogy suggests. Kip Thorne, meanwhile, was a theorist at Caltech, one of the world's leading experts on general relativity, a student of John Wheeler, who himself had been one of the great figures in 20th century physics. Thorne understood the theoretical side deeply. He knew what gravitational wave sources were out there, merging black holes, colliding neutron stars, supernovae. and he could calculate what their signals should look like. In the early 1970s, Thorne visited Weiss at MIT, and the two had a long, intense conversation about whether this interferometer idea could actually work. Thorne came away convinced. He went back to Caltech and decided to build an experimental gravitational wave program there. And that's where Ronald Drever comes in. Drever was a Scottish experimental physicist from the University of Glasgow, and he was brilliant in the way that the best experimentalists are. He had an almost intuitive feel for how to make instruments work better. He'd been working on resonant bar detectors, the older technology for gravitational wave detection that Joseph Weber had pioneered in the 1960s. But Drever quickly saw that interferometry was the future. Thorne recruited him to Caltech in the early 1980s to lead the experimental effort there. And this is where the human drama really begins, because Drever and Weiss were both strong-willed, opinionated experimentalists with very different working styles, and they clashed, repeatedly, sometimes bitterly. Drever was known for having a dozen ideas before breakfast, constantly wanting to redesign and improve things, resistant to being pinned down to a fixed plan. Weiss was more systematic, more focused on getting the engineering right step by step. Both approaches had merit, but trying to get them to work together on a single unified project was, by many accounts, extraordinarily difficult. By the mid-1980s, it was clear that detecting gravitational waves would require a massive, coordinated effort, not just a university lab project, but something on the scale of a particle accelerator. The arms needed to be kilometers long to have any hope of sensitivity. You'd need 2 detectors, separated by thousands of kilometers, so you could confirm that a signal was real and not just local noise. The cost would be hundreds of millions of dollars. This was big science, and big science needs management, organization, clear decision-making. In 1987, after years of internal friction, Caltech and MIT brought in Rochus Vogt as the first director of the LIGO project. Things moved forward. A proposal went to the National Science Foundation, and in 1990, Congress approved initial funding. But the internal tensions didn't go away. Drever was eventually removed from the leadership, a painful episode that left lasting scars. In 1994, the NSF essentially demanded a management shakeup, and Barry Barish, a particle physicist from Caltech with extensive experience running large-scale experiments, was brought in to lead the project. And here's the thing about Barish. He might be the person most responsible for LIGO actually getting built. He transformed it from what had been, frankly, a somewhat chaotic collaboration between feuding physicists into a properly managed, large-scale scientific project. He established clear milestones, organized the collaboration, brought in hundreds of additional scientists and engineers, and, critically, he structured LIGO in 2 phases. The first phase, initial LIGO, would build the detectors and prove the technology worked at a certain sensitivity level. Everyone knew initial LIGO probably wouldn't be sensitive enough to actually detect gravitational waves, but it would demonstrate the concept and develop the infrastructure. The second phase, advanced LIGO, would upgrade the detectors to a sensitivity roughly 10 times better, which would increase the volume of space they could survey by a factor of 1,000. Because you're looking in 3 dimensions, so 10 times the range means 10 cubed, 1,000 times the volume. And at that sensitivity, the astrophysical models predicted that detections should actually happen. The engineering challenges were staggering at every level. The mirrors, they're called test masses, had to be the smoothest, most precisely shaped objects ever manufactured. We're talking about 40-kilogram cylinders of ultra-pure fused silica, polished to a smoothness of about 1 nanometer. If you scaled one of these mirrors up to the size of the Earth, the largest bump on its surface would be about a centimeter tall. The mirrors hang from quadruple pendulum suspensions made of fused silica fibers, each thinner than a human hair, designed to isolate them from seismic vibrations. The vacuum system is one of the largest in the world. The beam tubes are about 1.2 meters in diameter and 4 kilometers long, and the air inside is pumped out to about 1/1,000,000th of atmospheric pressure. If you didn't do that, air molecules bouncing off the laser beam would create noise that would completely swamp the signal. The laser itself is a thing of beauty. It starts as a small, stable laser, then gets amplified to about 200 watts. But here's what's really clever. The light bounces back and forth inside the arms about 300 times before recombining, which effectively multiplies the arm length. So while each arm is physically 4 kilometers long, the light travels about 1,200 kilometers in each arm. And then there's a technique called power recycling, where light that would otherwise be wasted is fed back into the interferometer, boosting the effective power to something like 750 kilowatts circulating inside the arms. All of this to squeeze out every last bit of sensitivity. They built 2 detectors, one in Livingston, Louisiana, and one in Hanford, Washington, separated by about 3,000 kilometers. The separation is crucial. A real gravitational wave, traveling at the speed of light, would hit one detector a few milliseconds before the other, and the signal should look the same in both, just shifted in time. Local noise, on the other hand, an earthquake, a logging truck, someone slamming a door, would only show up in one detector. So you only believe a signal if both detectors see it, with the right time delay. Initial LIGO ran from 2002 to 2010. It reached its design sensitivity, which was an extraordinary engineering achievement in itself. But as expected, it didn't detect any gravitational waves. Then came the upgrade to advanced LIGO, which took about 5 years. New mirrors, new suspensions, new laser, new seismic isolation. Essentially, everything was replaced or improved. And on September 14th, 2015, just 2 days after advanced LIGO had been turned on for its first observing run, 2 days, both detectors picked up a signal. Think about that timing. Decades of work, billions of dollars, careers spent, feuds endured, near cancellations survived, and then 2 days into the upgraded instrument's first run, there it was. The signal arrived at Livingston first, then 6.9 milliseconds later at Hanford. It lasted about 0.2 of a second, and it had a very distinctive shape, a chirp. The frequency started low, around 35 hertz, and swept upward rapidly to about 250 hertz before cutting off abruptly. If you converted it to sound, and people did, it sounds like a quick rising tone. Whoop. That's it. That's the sound of 2 black holes spiraling into each other and merging, roughly 1.3 billion light-years away. Each black hole was about 30 times the mass of our Sun. In the final fraction of a second before they merged, they were orbiting each other about 250 times per second, moving at roughly 60% the speed of light. And when they finally combined, about 3 solar masses worth of energy was radiated away as gravitational waves. 3 solar masses, converted entirely to energy via E equals mc squared. For a brief moment, that merger was radiating more energy than all the stars in the observable universe combined. And yet, by the time those waves reached Earth, after traveling for 1.3 billion years, they stretched LIGO's 4-kilometer arms by less than 1,000th the width of a proton. The signal matched the predictions of general relativity with extraordinary precision. Theorists had been running computer simulations of black hole mergers for years, solving Einstein's field equations numerically, because the math is far too complex for pencil and paper when you have two massive objects spiraling together in a fully dynamic spacetime. These numerical relativity simulations predicted exactly what the waveform should look like: the in-spiral phase, the merger, and then the ring down, where the newly formed larger black hole vibrates and settles into its final shape like a struck bell. The observed signal matched those templates beautifully. It was general relativity, confirmed in the most violent, extreme conditions imaginable: strong gravity, high velocities, wildly dynamic spacetime. Exactly where you'd most expect the theory to break down if it were going to break down anywhere. The discovery was announced on February 11th, 2016, and it was front-page news around the world. Weiss, Thorne, and Barish shared the 2017 Nobel Prize in Physics. Drever, sadly, had developed dementia and passed away in March 2017, just months before the Nobel announcement. He was not included in the prize, and many in the community felt his contributions deserved recognition. It's one of those bittersweet notes that seem to follow so many great scientific stories. But LIGO didn't stop with that first detection. In August 2017, both LIGO detectors and the European Virgo detector picked up something different. Not two black holes, but two neutron stars spiraling together. And because neutron star mergers produce not just gravitational waves but also light, electromagnetic radiation across the entire spectrum, astronomers were alerted within seconds. Telescopes around the world swung to look at the source, and they saw it. A kilonova, a burst of light powered by the radioactive decay of heavy elements freshly forged in the collision. This was the first time an astronomical event had been observed in both gravitational waves and light simultaneously, and it opened up what people now call multi-messenger astronomy. And here's a detail that I find quietly astonishing. The spectroscopic analysis of that kilonova showed the signatures of heavy elements like gold, platinum, and uranium being created in real time. It turns out that a significant fraction of the heavy elements in the universe are forged not in supernovae, as we long assumed, but in neutron star mergers. The gold in a ring on your finger may well have been created in a collision between two neutron stars billions of years ago, flung out into space, eventually incorporated into the cloud of gas and dust that collapsed to form our solar system. General relativity predicted the waves that led us to watch that happen. And this brings us to something that Einstein himself spent decades thinking about, but never quite resolved: the relationship between gravity and the other forces of nature, and in particular, what happens when general relativity meets quantum mechanics. Because as triumphant as general relativity has been, Mercury's orbit, light bending, gravitational time dilation, GPS corrections, gravitational waves, black hole mergers, there are places where it breaks down. And that's not a minor footnote. It's one of the deepest unsolved problems in all of physics. So let's talk about where general relativity fails and why that failure is so profoundly strange. The issue isn't that general relativity gives wrong answers in everyday situations. It doesn't. For everything from planetary orbits to the large-scale structure of the cosmos, it works beautifully. The problem shows up at the extremes, at the very smallest scales and the very highest densities, places where you'd need both general relativity and quantum mechanics to describe what's happening, and where the two theories, when you try to combine them, essentially start screaming at each other. Let me set this up properly, because it's worth understanding why this clash is so fundamental. Quantum mechanics, developed in the 1920s and 1930s by people like Heisenberg, Schrödinger, Dirac, and Born, describes the behavior of matter and energy at the atomic and subatomic scale. It's spectacularly successful. Every piece of modern electronics you've ever touched, your phone, your laptop, the LED lights in your room, relies on quantum mechanics being correct. It describes a world where particles don't have definite positions until measured, where energy comes in discrete packets, where uncertainty isn't just a limitation of your instruments, but a fundamental feature of reality itself. And the other three forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, have all been successfully described in quantum mechanical terms. They've been reformulated as quantum field theories, where forces are mediated by the exchange of particles. Photons carry the electromagnetic force. Gluons carry the strong force. W and Z bosons carry the weak force. This framework, the standard model of particle physics, is one of the most precisely tested theories in the history of science. Some of its predictions have been confirmed to 10 or 12 decimal places. But gravity? Gravity has stubbornly refused to fit into this framework. And here's the thing. It's not for lack of trying. Physicists have been attempting to construct a quantum theory of gravity since the 1930s. The most straightforward approach would be to do what worked for the other forces. Treat gravity as a quantum field, with its own force-carrying particle. That hypothetical particle even has a name, the graviton. It would be massless, travel at the speed of light, and have a spin of 2, which is a quantum mechanical property that determines how it interacts with other particles. And at low energies, this approach actually works fine. You can write down a quantum field theory of gravity that gives sensible answers for weak gravitational fields, the kind you encounter in normal situations. The disaster happens when you try to push the theory to high energies. In quantum field theory, you have to account for all the possible ways particles can interact, including virtual particles popping in and out of existence at every energy scale. For the other forces, there's a mathematical technique called renormalization that lets you tame these contributions. You can systematically absorb the infinities that show up in your calculations into a finite number of measurable quantities, and the theory gives you finite, testable predictions. But when you try to renormalize quantum gravity, it doesn't work. The infinities multiply. At every order of calculation, new types of infinity appear that can't be absorbed, and the theory becomes what physicists call non-renormalizable. It doesn't just give you wrong answers. It gives you no answers. The mathematics collapses into meaninglessness precisely where you need it most. Now, you might wonder, where exactly does this matter? Where in the actual universe do you encounter conditions so extreme that you'd need a quantum theory of gravity? And the answer is, in at least 2 places that we know of. The first is the interior of black holes. The second is the very beginning of the universe. Let's start with black holes because they illustrate the problem beautifully. General relativity predicts that when a sufficiently massive star runs out of fuel and collapses, nothing can stop the collapse. The matter falls inward. The curvature of spacetime increases without limit, and you end up with what the mathematics describes as a singularity, a point of infinite density and infinite curvature, where the equations of general relativity themselves blow up. They give you infinity as an answer, and infinity isn't a physical answer. It's a cry for help from the mathematics. It's the theory telling you, I've been pushed beyond my domain of validity, and I can no longer describe what's happening here. And this isn't some exotic edge case. We know black holes exist. We've detected their gravitational waves. We've even imaged the shadow of one. In 2019, the Event Horizon Telescope collaboration produced that now famous image of the supermassive black hole in the galaxy M87, a dark void ringed by glowing hot gas, looking exactly like general relativity predicted it would look from the outside. But what happens at the center, behind the event horizon, at the singularity itself? General relativity can't tell us, and quantum mechanics, as currently formulated, can't handle the extreme gravitational conditions there. We need a theory that does both, and we don't have one. The event horizon itself is worth lingering on for a moment, because it's where some of the most fascinating paradoxes arise. The event horizon is the boundary around a black hole beyond which nothing, not even light, can escape. It's not a physical surface. There's nothing there you could touch or stand on. It's a mathematical boundary in spacetime, a point of no return. If you were falling into a large enough black hole, you might not even notice crossing it. Locally, spacetime would seem perfectly normal, but you'd be trapped, inexorably falling toward the singularity. Here's where things get really interesting. In the early 1970s, Jacob Bekenstein, then a graduate student of John Wheeler at Princeton, proposed something radical. He suggested that black holes have entropy, that they carry information about all the matter that has fallen into them, and that this entropy is proportional to the area of the event horizon, not the volume enclosed by it. This was a strange idea. In every other physical system, entropy scales with volume. You double the size of a box of gas, you roughly double the entropy. But Bekenstein argued that for black holes, it's the surface area that matters. Stephen Hawking initially resisted this idea, but in 1974, he made a discovery that changed everything. Using a semi-classical approach, applying quantum field theory in the curved spacetime around a black hole, without trying to quantize gravity itself, Hawking showed that black holes aren't perfectly black. They emit radiation, very faintly, very slowly, but they emit. This is Hawking radiation, and it arises because of quantum effects near the event horizon. In quantum mechanics, the vacuum isn't truly empty. It's a seething foam of virtual particle-antiparticle pairs constantly popping into and out of existence. Near the event horizon, one particle of such a pair can fall in while the other escapes, and to a distant observer, it looks like the black hole is radiating. Over immense timescales, far longer than the current age of the universe for stellar mass black holes, this radiation would cause the black hole to slowly shrink and eventually evaporate entirely. And this creates a paradox that has haunted theoretical physics for 50 years. If a black hole forms, swallows a bunch of matter carrying detailed quantum information about its state, and then evaporates away into featureless thermal radiation, what happened to the information? In quantum mechanics, information is never truly destroyed. The evolution of a quantum system is unitary, meaning it's reversible in principle. You could, in theory, reconstruct the initial state from the final state. But Hawking's calculation seemed to show that the radiation carries no information about what fell in. The information is apparently lost, and that violates one of the deepest principles of quantum mechanics. This is the black hole information paradox, and it's not a minor technical puzzle. It strikes at the foundations of physics. Either quantum mechanics is wrong about information conservation, or general relativity is wrong about what happens at the event horizon, or our understanding of both theories needs to be modified in some deep way. Hawking himself initially argued that information was truly lost, and he made a famous bet with Caltech physicist John Preskill in 1997 over the issue. In 2004, Hawking conceded the bet, saying he'd come to believe information is preserved, encoded in subtle correlations in the Hawking radiation. But the precise mechanism by which this happens remains unclear, and different approaches to quantum gravity offer different answers. This brings us to the other place where we desperately need a quantum theory of gravity, the Big Bang. If you run the expansion of the universe backward in time using general relativity, everything converges. Galaxies crowd together, the universe gets denser and hotter, and as you approach time zero, you hit another singularity. The density becomes infinite, the curvature becomes infinite, and general relativity breaks down completely. The theory can describe the universe from a tiny fraction of a second after the Big Bang onward, and it does so with remarkable accuracy. But it cannot describe the moment itself, or whatever came before it. That first sliver of time, roughly the first 10 to the minus 43 seconds, known as the Planck epoch, is where quantum gravitational effects would dominate, and we simply don't have the theoretical tools to describe it. Think about what that means. The most fundamental question you could ask about cosmology, how did the universe begin, and why does it have the properties it has, requires a theory of quantum gravity to answer. And we don't have one, but it's not as though people haven't been working on it. Several major research programs have been pursuing a quantum theory of gravity for decades, and while none has succeeded in the sense of making testable predictions that have been confirmed, they've produced extraordinary insights. The most famous is string theory, which emerged in the late 1960s and early 1970s, initially as an attempt to describe the strong nuclear force, and was later reinterpreted as a potential theory of everything, including gravity. The basic idea is that the fundamental constituents of nature aren't point particles, but tiny, one-dimensional vibrating strings, and different modes of vibration correspond to different particles. One of those modes naturally has the properties of the graviton, massless, spin 2, which means gravity emerges automatically from the theory. That was a remarkable discovery, made in the early 1970s by Joel Shirk and John Schwartz, and it's one of the main reasons string theory has attracted so much attention. It doesn't just accommodate gravity, it demands it. But string theory comes with complications. For the mathematics to be consistent, it requires extra spatial dimensions, 6 or 7 beyond the 3 we experience, which must be compactified, curled up so small that we can't detect them directly. The number of possible ways to compactify these dimensions is staggeringly large. Estimates suggest something like 10 to the 500 different possible configurations, each corresponding to a different possible universe with different physical laws. This is the string theory landscape, and it has made it extraordinarily difficult to extract unique, testable predictions. The other major approach is loop quantum gravity, which takes a very different philosophy. Instead of adding new ingredients like strings and extra dimensions, loop quantum gravity tries to apply quantum mechanics directly to general relativity's description of spacetime itself. It was developed starting in the mid-1980s by Abhay Ashtekar, Lee Smolin, Carlo Rovelli, and others. The key insight is that spacetime, at the Planck scale, distances of about 10 to the minus 35 meters, may not be smooth and continuous as general relativity assumes, but instead has a discrete, granular structure, like a fabric woven from tiny loops. Space itself comes in indivisible quanta, the smallest possible volumes and areas. And one of the most appealing features of loop quantum gravity is that it naturally resolves the singularity problem. In loop quantum cosmology, the Big Bang singularity is replaced by a big bounce, where a previously contracting universe reaches a maximum density and then expands again, avoiding the infinite density that plagues the classical theory. Neither of these approaches, nor several others, like causal set theory or asymptotic safety, has yet produced a prediction that distinguishes it from general relativity in a way we can currently test. The energies and scales where quantum gravity effects become important are so far beyond what our particle accelerators can reach that direct experimental tests seem for now almost impossibly remote. The Planck energy is about 10 to the 19 giga-electron volts. The Large Hadron Collider at CERN operates at about 10 to the 4. That's a gap of 15 orders of magnitude. It's as if you're trying to study the structure of atoms, but the best microscope you have can only resolve objects the size of a small country. You can see the country on a map. You know it's there, but the atoms inside it? Completely invisible to you at that resolution. That's roughly the situation physicists find themselves in when they try to test quantum gravity. And it's frustrating, because the theories are beautiful, they're mathematically rich, and some of the smartest people alive have spent decades developing them. But nature has put the answer behind a wall that our current technology simply cannot climb. So does that mean we're stuck? Does that mean quantum gravity is permanently out of reach, forever a matter of theoretical speculation and philosophical preference? Well, here's where things get a little more hopeful than you might expect. Because physicists are creative, and when the direct route is blocked, they look for indirect ones, clever end runs, unexpected windows, places where quantum gravity might leave fingerprints even at energies far below the Planck scale. One of the most promising places to look is the cosmic microwave background, that faint glow of radiation left over from when the universe was about 380,000 years old. You've probably heard of it. It's that speckled map of the baby universe that shows up in every cosmology documentary. The thing about the cosmic microwave background is that it carries information about the very earliest moments of the universe. Moments when the universe was so small and so hot that quantum gravity effects might have mattered. The idea is that during inflation, that brief period of exponentially rapid expansion that most cosmologists believe happened in the first tiny fraction of a second, quantum fluctuations were stretched to cosmic scales. Those fluctuations became the seeds of all the structure we see today: galaxies, clusters, voids, everything. And if quantum gravity influenced the nature of those initial fluctuations, even subtly, it might have left a signature in the patterns of the cosmic microwave background. Now, the signatures people are looking for are incredibly faint. We're talking about subtle statistical patterns in the polarization of the microwave background, particularly a type called B-mode polarization. Some models of quantum gravity predict specific modifications to the spectrum of primordial fluctuations, tiny deviations from what standard inflation would produce. The challenge is that these deviations are small, and they can be mimicked by other effects, like foreground dust in our own galaxy. The BICEP-2 experiment learned this the hard way in 2014, when they announced the detection of primordial B-modes with great fanfare, only to discover that what they'd seen was largely due to galactic dust. It was a painful episode, but it sharpened the field's understanding of what they need to do. Current and upcoming experiments, BICEP Array, the Simons Observatory, and eventually the planned CMBS-4 project, are designed to be far more sensitive and to disentangle the cosmological signal from the foreground contamination. Whether they'll see quantum gravity signatures specifically is an open question, but the window is there. Another indirect approach involves gravitational waves, and this is where the story circles back to LIGO in a beautiful way. Remember, LIGO detected gravitational waves from merging black holes and neutron stars. Those events happen in regions of extreme gravity, where space-time curvature is enormous. If quantum gravity modifies the behavior of space-time in those extreme conditions, it might leave imprints on the gravitational wave signal, tiny corrections to the waveform that general relativity alone wouldn't predict. As gravitational wave detectors get more sensitive, the next generation includes the Einstein telescope planned for Europe and Cosmic Explorer proposed for the United States, both aiming for sensitivity roughly 10 times better than current LIGO. Physicists will be able to measure the waveforms from merging compact objects with extraordinary precision. And with that precision comes the ability to test general relativity in the strong field regime more stringently than ever before. If there are deviations, even small ones, they'd be revolutionary. There's also the possibility of using black holes themselves as laboratories. The Event Horizon Telescope, which gave us that remarkable image of the M87 black hole's shadow in 2019, has continued to improve. In 2022, they released an image of Sagittarius A star, the supermassive black hole at the center of our own Milky Way. As the resolution and sensitivity of these observations improve, potentially with space-based extensions of the telescope array, astronomers will be able to map the geometry of spacetime near the event horizon with increasing fidelity. General relativity makes very specific predictions about the size and shape of the black hole shadow, the behavior of orbiting matter, the timing of hot spots circling the event horizon. Any deviation from those predictions would be a signpost pointing toward new physics. It's indirect, yes, but it's real data from the most extreme gravitational environments in the universe. And then there are tabletop experiments, which is a phrase that sounds almost absurd in this context. How could you study quantum gravity on a table? But there's a growing community of physicists exploring whether it's possible to detect quantum gravitational effects using very small, very precisely controlled systems, tiny masses placed in quantum superpositions, for instance. The idea, championed by physicists like Sugato Bose and Chiara Marletto, is that if gravity is truly quantum, then two small masses, each placed in a superposition of being in two different locations, should become entangled through their gravitational interaction. Detecting that entanglement would be evidence that the gravitational field itself is quantized, that gravity isn't just a classical background, but a genuine quantum entity. These experiments are extraordinarily challenging. The masses need to be small enough to put into superposition, but large enough for their gravitational interaction to be measurable. We're talking about masses on the order of micrograms to milligrams, held in superposition for long enough to accumulate a detectable gravitational phase. The technical hurdles are immense, isolating the system from vibrations, electromagnetic interference, thermal noise. But the proposals are being taken seriously, and several groups around the world are working toward making them a reality. If they succeed, it would be one of the most profound experimental results in the history of physics. Not a full theory of quantum gravity, perhaps, but proof that gravity is quantum at all, which is something we currently assume, but have never actually verified. Here's the thing that's worth sitting with for a moment. General relativity, this theory that Einstein finished in November 1915, has now been tested and confirmed in so many different ways across such a vast range of scales that it's almost hard to believe it started as one person's thought experiment about falling elevators. Think about the journey. It began with a puzzle about Mercury's orbit, a tiny discrepancy of 43 arc seconds per century that Newtonian gravity couldn't explain. It led through the equivalence principle, through years of mathematical struggle with tensors and differential geometry, to a set of field equations that reimagined gravity as the curvature of space-time itself. And then, one by one, the predictions came true, the bending of starlight, confirmed in 1919. Gravitational redshift, confirmed by Pound and Rebka in 1959. Gravitational time dilation, confirmed by Haffel and Keating with atomic clocks on airplanes in 1971, and now measured at the scale of 33 centimeters by optical clocks. The expansion of the universe, implied by the equations and confirmed by Hubble's observations. Frame dragging, confirmed by Gravity Probe B. Gravitational waves, predicted in 1916, doubted for decades, and finally detected in 2015. Black holes, once considered mathematical curiosities, now photographed. Neutron star mergers, observed simultaneously in gravitational waves and light, confirming that gravitational waves travel at the speed of light to extraordinary precision. Every single test, every single observation has confirmed Einstein's theory. Not approximately, not sort of, precisely. And this is a theory that was created primarily through pure thought, through imagining what the universe must be like if certain principles are true, and then finding the mathematics to express it. There's something almost unreasonable about how well it works. And yet we know it can't be the final answer. We know this because of those singularities, the places where the theory predicts infinite densities and infinite curvatures, which are really the theory's way of saying, I don't know what happens here. We know it because general relativity and quantum mechanics, the two most successful theories in the history of physics, speak different languages and refuse to be combined in any straightforward way. We know it because the universe appears to be filled with dark matter and dark energy, making up roughly 95% of the total energy content of the cosmos, and while general relativity accommodates them, it doesn't explain them. Dark energy, in particular, has a fascinating connection to general relativity. Remember that cosmological constant, the term Einstein added to his field equations in 1917 to keep the universe static, and then supposedly called his greatest blunder after Hubble discovered the expansion? Well, in 1998, two teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, discovered something no one expected. They were measuring the distances and redshifts of distant Type 1a supernovae, using them as standard candles to map the expansion history of the universe. What they found was that the expansion isn't slowing down, as everyone had assumed it would be, pulled back by the mutual gravitational attraction of all the matter in the universe. Instead, the expansion is accelerating. The universe is flying apart faster and faster, and the simplest way to account for this within general relativity is to bring back Einstein's cosmological constant, a constant energy density filling all of space, pushing things apart. The discovery won Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. And it means that Einstein's so-called greatest blunder might have been one of his most prescient insights, just for the wrong reason. But here's the deep puzzle. When you try to calculate the value of the cosmological constant using quantum field theory, adding up the energy of all the quantum fluctuations in the vacuum of space, you get an answer that is roughly 120 orders of magnitude too large. That's not a small discrepancy. That's 10 to the power of 120. It is, by some measures, the worst prediction in the history of physics. The observed value of the cosmological constant is tiny, exquisitely tiny, just barely enough to make the expansion accelerate. Why is it so small, but not zero? Nobody knows. This is sometimes called the cosmological constant problem, and it sits right at the intersection of general relativity and quantum mechanics, taunting us. So general relativity, for all its extraordinary success, is pointing us towards something deeper. It's like a map that's incredibly accurate for the territory it covers, but whose edges dissolve into blank space marked, "Here be dragons." The singularities, the dark energy puzzle, the incompatibility with quantum mechanics. These aren't failures of the theory so much as signposts. They're telling us where to look next. And what's remarkable is how many of those signposts are now becoming observationally accessible. We live in a golden age of gravitational physics. Gravitational wave observatories are being upgraded and expanded. Black hole imaging is improving year by year. Precision measurements of time dilation are reaching sensitivities that would have seemed like science fiction 20 years ago. Cosmological surveys are mapping the distribution of matter in the universe with unprecedented detail, looking for subtle deviations from general relativity's predictions on the largest scales. The next few decades could bring surprises that reshape our understanding as profoundly as Einstein's work reshaped Newton's. And in a way, that's the most beautiful thing about this whole story. General relativity didn't end physics. It opened doors. It revealed that the universe is stranger, more dynamic, more deeply interconnected than anyone had imagined. Spacetime isn't a stage. It's a participant. Mass and energy don't just exist within the universe. They shape it, curve it, make it ripple and sing. And somewhere in those ripples, in the quantum foam at the Planck scale, in the hearts of black holes and the first instant of the Big Bang, there are answers waiting. Answers to questions we're only now learning how to ask. And maybe that's the right place to let this whole story settle. Not with an ending, but with an opening. Because that's what general relativity has always been. Not a closed book, but an invitation. Think about where we started tonight. We started with Newton, with a picture of gravity that worked beautifully for over 2 centuries, apples falling, moons orbiting, cannonballs arcing through the air. And it worked so well that when something didn't quite fit, when Mercury's orbit wobbled in a way that Newton's equations couldn't explain, the smartest astronomers in the world assumed the problem was with the universe, not the math. They went looking for a missing planet. They named it Vulcan. They spent decades searching for something that wasn't there, because the alternative, that Newton might be wrong, was almost unthinkable. And then along came this patent clerk in Bern, a guy who couldn't get a university teaching position, who'd been rejected by the academic establishment, and he had the audacity to rethink the very nature of space and time. Not because he had better telescopes or more data, but because he asked a different kind of question. What would it feel like to ride alongside a beam of light? What would happen if you were falling freely and couldn't tell the difference between floating in deep space and plummeting toward the Earth? Those thought experiments, those simple, almost childlike questions, led him to the most profound reimagining of reality since Newton himself. And here's what I love about that. It wasn't just mathematical cleverness, though the mathematics were extraordinary. It was a kind of deep physical intuition, a willingness to take the universe at its word, even when its word was strange. Light travels at the same speed for everyone. Fine. Then time itself must be flexible. A person in free fall feels no gravity? Fine. Then gravity isn't a force at all. It's the shape of space-time. These weren't small adjustments. These were complete overhauls of concepts that human beings had taken for granted for millennia. Space is absolute and unchanging? No, it's not. Time flows at the same rate everywhere? No, it doesn't. Gravity reaches across empty space and pulls things together? No, there's no pulling. There's just geometry. And the thing is, Einstein didn't get there in a flash of inspiration. We talked about those years between 1907 and 1915, the long, grinding struggle to turn the equivalence principle into a complete theory. The false starts, the collaboration with Marcel Grossman to learn the mathematics of curved spaces, Riemannian geometry, tensor calculus, tools that had been developed by mathematicians decades earlier for purely abstract reasons and were now turning out to be exactly the language the universe was written in. The moment in 1913 when Einstein thought he had the right equations and published them, only to realize they were wrong. The frantic weeks in November 1915 when he raced against David Hilbert to find the correct field equations, working so intensely that he described himself as beside himself with excitement, barely sleeping. And then, that moment. November 25th, 1915. The field equations of general relativity, complete and correct. 10 tensor equations, or really one elegant equation, linking the curvature of spacetime to the distribution of mass and energy within it. And the first thing he did was calculate Mercury's orbit. And it worked. 43 arc-seconds per century, explained perfectly, no missing planet needed. He later said his heart palpitated when he saw the result. After 8 years of struggle, the universe had said yes, but the universe had also said something else. It had said, "You have no idea how strange I really am." Because those field equations, once people started solving them, kept revealing things that nobody expected. Karl Schwarzschild, lying in a hospital bed on the Eastern Front in 1916, found a solution that described the spacetime around a single spherical mass, and buried in that solution was the possibility of what we now call a black hole, a region where spacetime curves so severely that nothing, not even light, can escape. Einstein himself didn't believe they could actually exist in nature. It took decades for physicists to accept that they were real, and more decades to observe them. But the math knew. The math had been telling us all along, and the equations predicted gravitational waves, ripples in spacetime itself, propagating outward at the speed of light when massive objects accelerate. Einstein predicted them, then tried to retract the prediction, then was corrected by a reviewer he initially resented. And those waves turned out to be real too, spectacularly confirmed a century later by LIGO, an instrument so sensitive it can detect a change in length smaller than 1/10,000th the diameter of a proton. Think about that. We built a machine that can feel the universe trembling. And gravitational time dilation, clocks running at different rates depending on how deep they sit in a gravitational field. Not by much, not in everyday life, but by enough that your GPS would drift by kilometers per day if it didn't account for general relativity. The satellites are literally living in a slightly different flow of time than you are, right now as you lie here. And those NIST experiments we talked about, measuring time dilation across a height difference of 33 centimeters, a single step on a staircase, that's not theoretical anymore. That's measured. That's real. Time genuinely passes at a different rate at the height of your head compared to the height of your feet. The difference is absurdly tiny, but it's there and we can detect it. Your feet are aging slightly more slowly than your face right now, because they're closer to the center of the Earth and deeper in its gravitational well. I know. It's wild. So general relativity has been confirmed over and over and over again, across more than a century, across scales ranging from tabletop experiments to the entire observable universe. Frame dragging, confirmed by gravity probe B, gravitational lensing, observed routinely by astronomers. The expansion of the universe, predicted by the equations before it was observed. Gravitational waves, detected directly. Black holes, imaged directly. First M87 in 2019, then Sagittarius A star in 2022. The supermassive black hole at the center of our own galaxy, 4 million times the mass of the Sun, sitting right there in the middle of the Milky Way, 26,000 light-years from where you're lying. And yet, for all of that, we know the theory is incomplete. We talked about why. The singularities, those points where the math breaks down, where curvature becomes infinite, where general relativity essentially throws up its hands and says, I can't describe what happens here. Every black hole has one at its center. The Big Bang was one, or something like one. And the theory's incompatibility with quantum mechanics, the fact that when you try to apply quantum rules to gravity the way you successfully apply them to every other force, you get nonsense. Infinities that can't be tamed, a breakdown at the Planck scale, at distances so small and energies so high that our current theories simply don't have the vocabulary. And dark energy, that mysterious something that's making the expansion of the universe accelerate. You can fit it into general relativity by putting a cosmological constant into the field equations, Einstein's old biggest blunder, resurrected, but nobody can explain why it has the value it does. Quantum mechanics predicts a value that's roughly 120 orders of magnitude too large. That's not being off by a factor of 2 or 10. That's being off by a number with 120 zeros. It's arguably the worst prediction in the history of physics, and it's telling us something profound about the gap between our two best theories of reality. So where does that leave us? It leaves us, I think, in a position that's remarkably similar to where physics was in the late 1800s. Back then, Newtonian mechanics and Maxwell's electromagnetism were both spectacularly successful, but they were subtly inconsistent with each other. The speed of light was constant in Maxwell's equations, but shouldn't have been constant in Newton's framework. Most physicists assumed the inconsistency would be resolved with minor adjustments. Instead, it took a revolution: special relativity, then general relativity, then quantum mechanics. The whole foundation had to be rebuilt. We might be at a similar juncture now. General relativity and quantum mechanics are both spectacularly successful, but they're subtly, and sometimes not so subtly, inconsistent with each other. And the resolution probably won't come from minor adjustments to either one. It'll probably require something genuinely new. A deeper theory that contains both as limiting cases, the way general relativity contains Newtonian gravity as a limiting case. When gravity is weak and speeds are slow, Einstein's equations reduce to Newton's. Whatever comes next will need to reduce to general relativity when quantum effects are negligible, and to quantum mechanics when gravity is negligible. But in the regimes where both matter, inside black holes, at the Big Bang, at the Planck scale, it'll say something entirely new. What that something is, nobody knows yet. String theory, loop quantum gravity, causal set theory, asymptotic safety. These are all serious attempts, all mathematically rich, all pursued by brilliant people. But none of them has made a testable prediction that's been confirmed. Not yet. And that not yet is important, because, as we talked about, the experimental tools are getting better. The gravitational wave detectors are getting more sensitive. The black hole images are getting sharper. The cosmological surveys are getting deeper. The tabletop experiments are getting more precise. Somewhere in all that data, there might be a clue, A tiny deviation from general relativity's predictions, a whisper of quantum gravity, a fingerprint of whatever deeper theory is waiting to be found. And you know, there's something deeply comforting about that. Not knowing, being at the edge. Because it means the story isn't over. Physics isn't finished. The universe still has secrets, and we're still clever enough, still curious enough, still stubborn enough to go looking for them. Einstein didn't finish the story. He opened a chapter, an extraordinary, beautiful, mind-bending chapter. But the book goes on, and maybe that's the most important thing to carry with you as you drift off tonight. Not any particular equation or experiment or date, but this. The universe is comprehensible. That's not obvious. There's no reason, no guarantee, that the laws governing the behavior of space-time and matter should be expressible in mathematics that human beings can understand. But they are. Einstein marveled at this. He called it the most incomprehensible thing about the universe, that it is comprehensible. A mind that evolved to track prey on the African savanna, to judge the ripeness of fruit, to navigate social hierarchies in small groups. That same mind can deduce the curvature of space-time around a black hole, can predict the frequency of gravitational waves from colliding neutron stars 100 million light-years away, can measure the rate at which time itself flows differently at different heights above the Earth. That's astonishing. That's the deepest mystery of all, in some ways. So let it settle. All of it. Newton's falling apple and Einstein's falling elevator. The bending of starlight during a solar eclipse in 1919. Clocks on satellites ticking faster than clocks on the ground. Space-time rippling when two black holes spiral into each other 1 billion light-years away. The shadow of a black hole, captured in radio waves by telescopes spanning the entire Earth. The accelerating expansion of the universe, driven by something we've named but don't understand. And somewhere beneath all of it, at the smallest scales and the highest energies, a deeper truth waiting to be uncovered. You don't need to hold on to all the details. They'll be there when you want them. For now, just rest with the feeling of it, the sheer improbability and beauty of a universe that curves and ripples and flows, that bends time and stretches space, that hides singularities behind event horizons and scatters galaxies across an expanding cosmos. A universe that, against all odds, we can understand. Partially, imperfectly, but genuinely. We can understand it. And we're still learning. That's enough for tonight. That's more than enough. Let it all go soft and quiet now, like starlight crossing the vast, gently curving space-time between there and here, taking its time in no hurry at all, just like you.